Hello and welcome to another lecture on understanding and describing numerical data. In this lecture, we're going to be talking in particular about robust statistics. In this lecture, we'll get into what robust statistics mean and cover some statistics which are robust, like the median as a statistic for representing the center of a distribution. As you may remember from math classes in your past, the median is a value that splits the data in half when the observations in the data set are listed in order. So if we observe 5 numbers, 10, 12, 14, 16, and 18, we have them listed in order from smallest to largest. The observation that is in the middle, in this case 14, is the median. When there are an even number of data points and no one number that's at the exact middle of the distribution, the median is the average of the middle 2 observations. So in this example, the middle 2 observations are 12 and 14. The average of 12 and 14 is 13. The median is also the midpoint of the data. So 50% of the values in the data set are below the median, and 50% of the values are above the median by definition. So the median is also the 50th percentile of the data. When we split our data into fourths, the dividing line between each of those fourths is called a quartile. So the 25th percentile is called the first quartile. That means that 25% of the data are below that point. Like we already said, the 50th percentile is the median, also called the second quartile. 50% of the data are below that point. And the 75th percentile is the third quartile, Q3, and 75% of the data are below that point. In between the first and the third quartile is what's called the interquartile range, or IQR. In between Q1 and Q3 is the middle 50% of the data. One way of graphically representing numerical data is to use what's called a box plot. A box plot gives us a lot of information about the distribution of our data. So for example, it gives us information about the range of the data, the low point and the high point of the data. So you can see that on the scale out to the left of this box plot. The middle box represents the middle 50% of the data, so the interquartile range, and the thick line in the middle of that box is the median of the data. So let's take a little bit closer look at the rest of the features of a box plot. So again, the box in the middle of the box plot represents the interquartile range, the middle 50% of the data. The lower bar of that box is a line that represents the first quartile, and the upper bar of the box represents the third quartile. So everything in between the first quartile and the third quartile is the interquartile range. And again, the line in the middle of the box is the median, or the second quartile. Extending out from the box, you have these lines that reach up, and then the horizontal lines at the end of that line. Those lines are called whiskers, the lower whisker and the upper whisker. And on the next slide, I'm going to describe how those whiskers are defined. And then finally, above the upper whisker in this box plot, we see some suspected outliers. Outliers could be above the upper whisker, or they could be below the lower whisker. But the outliers are data points that are sort of unusual and very different from the rest of the data points in our sample. You can see beside the box plot to the left is a bunch of dots that represent the actual distribution of the data. So you can see how the bulk of the data are centered on between the upper whisker and the lower whisker, and those observations that are above the upper whisker seem pretty unusual. So we're going to call those outliers. Okay, now let's talk about how we define those upper and lower whiskers. So we have a mathematical formula for determining how far away from the central box the whiskers of the box plot can extend. That formula is 1.5 times the interquartile range. Now remember, the interquartile range is the range of the middle 50% of the data. So to find the IQR, you take the value of Q3, so the line that divides the third quartile from the rest of the data, and the value of Q1, and you take Q3 minus Q1, and what's left over is the interquartile range. So the maximum reach of the upper whisker is 1.5 times the interquartile range above Q3, and the maximum reach of the lower whisker is 1.5 times the IQR below Q1. And again, a potential outlier is an observation that is beyond the maximum reach of either the upper whisker or the lower whisker. So these are observations that have pretty extreme values relative to the rest of our data, and they're located above the upper whisker or below the lower whisker in the box plot. So why should we pay attention to unusual observations, to observations that have extremely different values from the rest of the data in our sample? Why are we not just treating these observations like any other? Well, there are a couple of reasons. First is to identify if the distribution is extremely skewed. That can be worthwhile to know in terms of the shape of the distribution. Another reason we might take a look at outliers is because those outliers might be an accident. They might have happened because of an error in data collection or data entry. For example, if you had an extreme outlier in the age variable, where someone's age was recorded as 400 years old, we can probably conclude that that's an outlier that we need to get rid of in the data because that subject is not actually 400 years old. Probably it was just a miscoding of someone who is maybe 40. And the final reason is that outliers are interesting. Because they're extreme observations, we should be paying attention to them and thinking about where they're coming from, if they're an interesting feature of the data that we have. So let's talk about a brief example to help illuminate some of the concepts that we've been talking about. In this example, we have 4 people sitting at a bar at your local pub. In seat 1, Anne. Anne makes $54,000 a year. In seat 2, Manuel, who makes $80,000 a year. In seat 3, Joe, who makes $46,000 a year. And in seat 4, Tracy, who makes $25,000 a year. So the mean, the average yearly income for these people is $51,250. Now let's consider what happens when a 5th person comes into the bar and has a seat. And the 5th person is Bill Gates. Now, Bill Gates' annual income is around $11.5 billion a year. So what effect is this going to have on the mean income for the people at the bar? When we add up these 5 incomes, what we end up with is finding that the average income for these 5 people is around $2.3 billion a year. Unfortunately, that $2.3 billion a year is not evenly distributed across all 5 people in their sample, much to the chagrin of everyone who is not Bill Gates. What this tells us is that the mean is really sensitive to outliers. But another measure for capturing the middle of a distribution, the median, is not sensitive to outliers. So let's take a look at this by examining the distributions for before Bill Gates walks into the bar and after Bill Gates walks into the bar. So before Bill Gates enters, the mean of the distribution of the 4 people there is $51,250, and the median is really close to that. It's $50,000, is the middle of the distribution as calculated by the median. After Bill Gates enters the bar, the mean jumps up by a substantial amount and becomes $2.3 billion. But the median only goes up a little bit to $54,000. So the observation that is in the middle of the data is still only $54,000 and still represents the people in the bar pretty well. So while the mean is a statistic that is very sensitive to outliers, the median is robust to outliers. It is a robust statistic for estimating the middle of a distribution. The median and the interquartile range are more robust to skewness and to outliers than the mean and the standard deviation. So what this means is that when we have a symmetric distribution without extreme outliers and without skewness in one direction or the other, the mean and the standard deviation are really good ways to capture both the center of the distribution as well as the spread of the distribution. But for skewed distributions, and distributions where there are extreme outliers, it can be a lot more helpful to take a look at the median and the interquartile range to describe the center and the spread of the distribution, because those statistics are not going to be changed so dramatically by the presence of outliers or the presence of skew. In a symmetric distribution, the mean and the median are just about equal. So we saw this when we were looking at our example of the incomes of people in a bar. Before Bill Gates walked in, that distribution was more or less symmetric, and the mean and the median were very close to one another. But when the distribution is skewed or has extreme outliers, the mean is going to get dragged in the direction of the skew or toward the outliers. So a right skewed distribution has a mean that is a lot greater than the median. So you can see this in the far right distribution in this graph here. In a left skewed distribution, where you have the tail of the distribution pointing out toward the left, the mean is going to be lower than the median. And again, the normal distribution in the middle, the mean and the median are going to be just about the same. So here's an example question for you to test your understanding of the concepts that we covered in this video. Take a look at this sample distribution and see if you can answer these questions. Is the distribution symmetric, right skewed, or left skewed? And do you think that the mean is about the same as the median? Do you think the mean is greater than the median? Do you think the mean is less than the median? Or is it impossible to tell? Because the long tail of this distribution stretches out to the left, that means that the distribution is left skewed. And as we talked about earlier in this video, when a distribution is left skewed, the mean is going to be less than the median. So the mean is going to get pulled out toward the left in the direction of the tail of the distribution, whereas the median is going to stay closer to the high point of the distribution. So here in the left skewed distribution toward the greater values of the distribution. So that's been our discussion about robust statistics as a way of describing a distribution. A robust statistic, again, is a statistic that is not sensitive to outliers and the skew of a distribution. So the median is a robust statistic for describing the center of the distribution. And we didn't go over this in much detail, but the interquartile range, a statistic that captures the middle 50% of the data, is not sensitive to points out at the edges of the distribution because it is only focused on the middle 50% of the data. You can compare that to a statistic like the variance or the standard deviation, which is just the square root of the variance. Those statistics are based on taking a look at the distribution of all of the data points and their relationship, how far away they are from the mean. So an extremely distant data point, an extreme outlier that's very far from the mean, is going to really increase the variance of the standard deviation. So you can understand why that statistic is not very robust to the presence of outliers or the presence of skew, or the interquartile range, because it only takes into account the middle 50% of the data and not those points at the edges, is going to be robust. So these videos have been talking about how we describe numerical data. Next up, we're going to talk about different ways that we can describe categorical data. So I will see you then.